Okay, good afternoon. So till now we have looked at design of columns. So columns under uniaxial, I'd say pure axial compression. So two types of problems we have seen. One is square column and then a rectangular or a circular column. So two problems we have seen and seen how we can design a given column for a axial load. Okay, so continuing from this today's class, we are seeing one step after it, which is columns with uniaxial bending. Columns with uniaxial bending. Okay, so like this, we will usually be given some details. One of the main details that you will be given is the first thing that you need to be given is what is the load you have to design for. Okay, so in this example, we'll have a look at a load of these are all factored or they are factored loads. Yeah, factored loads. Okay, so factored loads. I'm having axial compression is 140 tons or 1400 kilonewton, and bending or the ultimate. Actually, this can also be called as ultimate axial compression. Ultimate moment along one of the directions is 280 kilonewton meter. So for this combination, we need to design the given column, and some set of values can be used. So here it is, we are restricting ourselves to M20 and AC415. Okay, right. So let's make this column to be a rectangular one. Okay. Now the first question that I would ask is, I have compression and a certain bending moment along a certain direction. So when I draw this rectangle, which side should the length of that rectangle be more? We have a rectangle. So how do you decide which way to make the rectangle? Whether to make the rectangle, whether to make the rectangle like this or like this? How do you decide which way to place the rectangle?
Depends on the direction.
Depends
on the direction of the moment.
The direction of the moment. The reason being?
The moment of inertia will be
Exactly. So the moment of inertia perpendicular to the axis will be more. Okay, so basically what I mean is, so I have not specified which direction. So if this 280 kilonewton meter is going to be acting this way, okay, it's going to act about this axis, then perpendicular to this axis is this direction. So I need to make this longer. Okay, so that is how you decide which way to make the rectangle bigger. Next thing you want to decide is what size to give for the rectangle. Once again, here the easiest thing that you can do is just make a good reasonable assumption to the size of the column. Okay, so there is no one right answer. There are many sizes that you can adopt for a given moment and compression. Okay, so I can just assume some particular size, and later if you feel it is too much, you can obviously revise it. So let's assume the rectangle to be, this is the size that I'm assuming. I'm assuming 300 by 600. Okay, so this is the, going to assume it this way. Okay, so 300 by 600 is the assumed dimensions of the column. Or I can say call it as the preliminary dimensions. Okay, the word you use is preliminary, meaning that if it works out well, you will continue with it. If it doesn't work out well, you'll revise it. How many minimum bars should I give for this? Four. Okay, so let's say, oh fine, okay, 4. 1, 2, 3, 4. Is this fine or there's a problem with this?
The spacing should not exceed 300 meter. 300 mm.
Yeah, it should not exceed 300 mm. Okay, so if I keep it like this, the spacing between the bars, especially along this direction, will be more than 300 mm. So therefore, I cannot keep it like this. I need to give some more number of bars. Okay. So what I can say is, no, for example, you can, at this stage, you need not assume the diameter of what you're going to use, but if you're able to do it, fine. Otherwise, you can just say that, no, this to this distance will be about 500. So the minimum that I need in between is at least one more bar in the middle is needed. At least one more. So what I'll probably do is, let me make it a bit more compact. And this is obviously the choice that I'm making. You're allowed to restrict yourself to just one bar in the middle also. That is also allowed. But for some, just for my, as per my choice, I'm just giving 4 on top and 4 on bottom. Okay. So the logic that we use probably is, this is 300 and I use 2 bars. So this side being 600, I am using 4 bars. That's it. But you're allowed to just keep 1 bar in the middle also. That is also allowed instead of keeping 2 and 2. Both are okay. Right. So for this, this is a case of uniaxial bending, axial compression and uniaxial bending. So therefore, you cannot use the normal code formula. Okay, using it will be difficult. So therefore, the easiest thing to do here is to use SP16 1980 charts. Okay. So whenever you are given a problem of column width bending, even if it's not specified to you that use SP16, you are allowed to use SP16. For other things like beams and slabs or pure axial compression columns and all, unless I tell you that find it out using SP16, don't use SP16 to find it. Use the analytical equation unless you're otherwise specified. But for columns with bending, even if I don't specify it, you can still use SP16 because there's no other way to do it. There's no other easy way to do it. Okay, so let's let's have a look at how those charts look. And I think I have to share my full screen rather than sharing just the window. Okay, are you able to see my SP16?
Yes, sir.
Okay, so now if you have a look at SP16, this goes on for a lot of pages. Okay, the charts with respect to uniaxial bending, no, they go on for quite a lot of number of pages. So this one, page number 111 and 110. These two charts are for pure axial compression. So this is even using the formula is easy. So you don't have big advantage in using the chart. But if you want to use it, if you're asked to use it, you can use it. Then from page number 112, you start having a lot of charts. So they start with FI 250 and D dash by D ratio to be 0.05. Okay. And if you look at any of these charts, you will have on the y-axis PU by FCKBD, y-axis you will have MU by FCKBD square. Okay. And depending on the combinations of load and the moment that you have, you can choose any of these curves. Okay, you can choose any of these curves, and each of these curves represent a certain they represent a certain value of P by FCK. P, small p, not capital P, small p by FCK, where small p, I'll probably zoom it a bit. Okay, so what is shown over here is it's blurred because it's a photograph of SP16, unfortunately. So this is actually small p, meaning it's the percentage of steel. Okay, and divided by FCK equals some ratios 0.26, 0.24, 0.22, 0.20, like the way all the way till 0. Okay. So, so knowing the value of ultimate compression and ultimate moment, you can just use any of these curves. You know the value of FCK and you can pick out the percentage of steel that you require. So this is the only job in using these charts. Okay. Now, only thing is we need to pick out which chart you should use. So if I look at what I have done, I see that I have reinforcement along this side, a distribution of reinforcement along this side. There is no specific distribution along this edge and this edge. Okay, so by looking at this image itself, I see that it corresponds to a case like this where two edges alone the reinforcements are aligned. These two edges there are no there is no line of reinforcements along this edge and this edge. So we will be looking at reinforcement distributed equally on two sides. Okay, but anyway, we have FE415, so we cannot use any of these tables. So we'll just keep moving till we go to FE415. So this is FE415, and this is for d dash by d equals 0.05. Okay, so we might probably just want to use one of this. Okay, so let's assume that our d dash by d is also. Let's see how much it is. Okay, so this is d dash. If I assume 20 mm bars, if I say that these are all 20 diameter bars, in that case your effective cover equals clear cover plus dia by 2. So what is the minimum clear cover for a column? Anyone knows? 30. So 30, usually for columns they take a little more, they take about 40. Okay. But anyway, I have 600 over here. So let me say that I take no, even 50 mm clear cover. You just need to take the minimum and then add the diameter by 2, but you're allowed to take slightly larger for more conditions. Anyway, if you have any doubts regarding what size of clear cover you should use for beam, slab, column, foundation, etc., it's specified in IS 456, so you can just read it. You will know what you should give. So anyway, for this purpose, let me just give it as 40 plus 20 by 2, 10 equals 50. Okay, so my d dash by d is nothing but 50 by 600. So how much is 50 by 600?
.083.
0.083. So it is a bit inconvenient. It is falling in between 0.05 and 0.1. Okay, it's a bit inconvenient, but anyway, what you can do when we have such a situation is we can use the higher cover. Okay, so this is 0.05 means use 0.1's chart that will give you a more conservative value. So you can use this. Okay, so we have selected the chart. Next job is to evaluate PU by FCK B capital D and MU by FCK capital BD square. Okay, so this is an easy thing to do. PU by FCK B D square, and also find, sorry, BD only, and MU by FCK B D square. Remember, it's overall depth, not effective depth. Okay. B is usually the smaller one, and usually B is the direction along which, see, for example, so you need to know the meaning of B and D. So if I have this as the rectangle, and my moment is acting along this axis, then this should be taken as D. This should be taken as B. Okay. So in other words, usually we give the higher dimension for along the moment, no? So my D will be 600, B will be 300 according to this problem. So you can just find it out, what is PU by FCKBD and MU by FCKBD square. The values of PU and MU are given above, factored values, ultimate values. FCK is 20. So basically you have 1400 divided by 20 into 300 into 600, and here you have 280, 20 into 300 into 600 square. Yeah, so tell me what you get for these. So what is PU by FCKBD and MU by FCKBD square?
So
What's
0.389 for P by
which one? This one, huh? PU by FCKBD, yeah?
Yes, sir.
0.3.
0.389.
0.3, okay, fine. How about
For
this?
that, 0.129.
Okay, others also try, see if you get 0.389 and 0.129.
Yes, sir.
Did it right? Okay. So now you have these values, and now you can go back to your SP16, and once again I think I have to zoom it. So my PU by FCK BD was 0.389, which is probably somewhere here along this. I would like to have a so somewhere probably along this line is what I have for PU by FCK BD, and I have 0.129, which is probably somewhere here. Okay. So I see that I have an intersection at. So basically, where is this intersection? It is at this particular point. It's basically corresponding to P by FCK equals. இங்க இருக்கு. இது வந்து this is P by FCK equals 0.08, I suppose. Okay. 0. Yeah, it's at about 0.08. Okay, if I see the table there. Yeah. Okay. Yeah, I don't have much clarity in this table because it's a bit blurred. So I'm sorry if you're not able to see it clearly. 0.389 and 0.129. This is 0.32, 34, 36, 38, 0.38, somewhere here, okay. 0.129, 0.1, 0.12, 0.129. Okay, correct, 0.08 only. So I get P by FCK, small p not capital P. So from chart number, what is the number of the chart? 32, from chart 32. Chart 45, yeah. Oh, this is 4 6 actually. Okay. So chart 32 we have 0.08. Okay, or this gives me percentage of steel equals. So if P by FCK is 0.08, how much is P? FCK you know the value. So what do you think will be P?
1.6%.
Right?
1.6.
1.6. About 1.6% is the percentage of steel that you will require. So anyway, once this is known, then the remaining is easy. So then I can find the steel that I require. 1.6 into 300 into 600 by 100. How much is AC?
$2,880.
2880 mm square. Okay, and based on what I have given 8 number of bars going by this. So I need about approximately 1 bar to be. I need 1 bar to give me 2880 by 8. So how much is this? This will come about
360.
360. Yeah, okay. 360. So 360. What do we have? 201 is 16. 20 is 342. Yeah. Okay. This which is 342 is less than this. So therefore, let's say if I give 4 numbers of 1 minute. Hello. சொல்லுங்க சார். அந்த பிளேட் சார் ஓகே அந்த பிளேட் தானே நான் ஒரு ½ அன் ஹவர்ல கூப்பிடுறீங்களா? ஆமா. அப்படி அது நான் தர முடியாது. அப்படி போடுறதுல யூஸே இல்லை. 25ம் 6 நீங்க ஆமாங்க. அது சார் அது அவங்க சொல்லலைங்கிறதுனால தான் அவங்க என்னை கூப்பிட்டு இந்த மாதிரி 25 mm போடலாமான்னு கேட்டு என்கிட்ட கேட்டு ஃபுல்லாக நான் பார்த்து அதாச்சும் அந்த ஸ்கோப்பை மட்டும் நான் பார்த்து சொல்லியிருக்கேன். சரி 25 mm போட்டுக்கலாம், ஹிஞ்ச்டு பேஸ் எல்லாம் இன்சூர் பண்ணிட்டீங்கன்னா சொல்லி கொடுத்துருக்கேன். அப்போ திருப்பி வந்து அவர் 30 mm போடலாமான்னு கேட்குறாருன்னா வந்து அதுக்கு நான் அதுக்கு நீங்கள் அவங்க சிஐடியோட ரிப்போர்ட்டே யூஸ் பண்ணிருக்கலாமே, எதுக்கு திருப்பி ஒரு வாட்டி இதை செக் பண்ணுறது சொல்லுங்கள். ஆமாங்க, அந்த தடிமம் அவைலபிள் இருந்தான்னு சொல்லி நான் 25 mm நான் பார்த்து கொடுத்துருக்கேன் அவருக்கு. ஓகேங்களா? இப்போ நீங்க அதாச்சும் எப்படின்னா நானும் அந்த இந்த டவுட்ல தான் வேற ஒருத்தவங்களையும் போய் கேட்டேன். மசாலா பட் நீங்க பேசிருக்கீங்க நினைக்கிறேன், அவங்கள்ட்ட ஒரு வாட்டி கேட்டேன். அவங்க சொன்னாங்க இந்த மாதிரி 25ம் 6ம் சுற்றி வெல்ட் பண்ணி கொடுக்கறதுக்கும் 25 மட்டும் கொடுக்கறதுக்கும் ஒன்று தான். அந்த 6 வெல்ட் பண்ணி கொடுக்குற பிரயோஜனமே இல்லைன்னு சொன்னாங்க. இன்ஃபேக்ட் அந்த 6ல வெல்ட் பண்ணுறதுல வந்து ஹாரிசான்டல் மூவ்மெண்ட் வந்து அந்த வெல்ட் போச்சுன்னா தான் பிரச்சனை வழியுமே தவிர அதுக்கு நீங்கள் 25 mm கொடுத்துடலாம். அது இன்கேஸ் 30 mm கொடுக்கணும் அப்படின்னா வந்து நீங்கள் இந்த ரிப்போர்ட் இன்வாலிடேட் பண்ணிட்டு நீங்கள் சிஐடி ரிப்போர்ட்டை வந்து வச்சுக்க வேண்டியதான். அதுக்கு அவங்க சொன்னாங்கன்ட்டு. சரி, அது மூலமா அது பேமெண்ட் வந்துச்சு, அது பண்ணி கொடுத்தது பேமெண்ட், அது வந்து முடிஞ்சது. ஓகேங்களா? அவங்க இம்ப்ளிமெண்ட் பண்ணுறதுக்கு அவங்க 25 mm + 6 போடணும்னு அவங்க நினைக்கிறாங்கன்னா லெட் தம் ரிட்டர்ன் த ரிப்போர்ட். அவ்வளோதான். இல்லை, அது அது நீங்கள் பாருங்க, அது தட் இஸ் நீங்கள் டிசைட் பண்ணுறது தான் அது. ஓகேங்களா? நீங்கள் அப்படி டிசைட் பண்ணீங்கன்னா நீங்கள் அவங்க ரிப்போர்ட்டை வந்து பேசிஸாக வச்சுக்கோங்க. 25 போகிறீங்கன்னா என் ரிப்போர்ட்டை மட்டும் வச்சுட்டு அதை வச்சு நீங்கள் போடுறதா போடுங்க. அவ்வளோதான், வேற ஒன்றும் இல்லை நான் சொல்கிறதுக்கு. இது அப்புறம் அந்த இது மட்டும் ஜஸ்ட் சொல்லிடுங்க சார், இந்த கெனோப்பியோடது. கெனோப்பி சொல்லுங்க. ஓகே. சரிங்க சார். ஓகே. Okay. So 2880, I have 20 mm bar gives me 314 and 25 mm bar gives me 490. So this is less, this is too much more. So let me try something in between, and let me say I do 4 numbers of 25 and 4 numbers of 20. So 490 into 4, 980,960, 314 and 1,256. How much does this add up to? 6 1. I'm getting no. So 3 1. This is the summation, no? I think it is.
So 3216.
3216. Okay. Anyway, it's still a bit more. The other option, if I give 201, 314, 208. Actually, this is the only option. Okay. Or if I give 28 mm. So actually, this is okay. You can give 3216 for 2880, not a problem. It's anyway better than giving 8 numbers of 25. So only thing I'll probably search is I'll see if there's a even more economical solution. Though your one is perfectly allowed to use 3216. So 28. Pi into 15 square. 615. Okay, 615, 2400. Okay, anyway, I get the same. I think this is the best solution. Okay, so we can adopt 4 numbers of 25 and 4 numbers of 20 diameter bars. So how we'll arrange it is the exterior walls will be 28 diameter bars. So basically this and this will be 2 numbers of 28.5 and this and this will be 2 numbers of 20 diameter bars. So the reinforcement is done. Next is only to check the ties. Okay. So let's assume 8 diameter ties, and the conditions for giving the ties also I once already told in the last class. So basically the diameter of the ties should be greater than the greatest of these two, which is the diameter of the longitudinal bars by 4, and the next one is 6 mm. Okay, so ours is 25 diameter bar, Okay, so this is about 6.25 mm. So 8 mm is more than both of it. So 8 mm diameter can be used. And the spacing of the ties, once again, we also make that spacing to be lesser than the least of two conditions. One is 16 times the, which is the, by the way, 16 times the, which is the smallest diameter that we have is 20. So this is 16 times 20, which is 320 mm square, and 20 mm, and the other is 300 mm. Okay, so the least of this is this, so we have to give a less than or equal to 300 mm spacing. Okay, so let me say that provide 8 mm ties. So the limit is 300. Let me not. You are allowed to use 300, but if I want to be a bit safe, or if I am a bit if I'm a person with a lot of doubts always, then I can just maybe be a bit more safe. If I let me reduce it a bit and say 250 center to center. I have not reduced this from 300 to 250 based on any provable scientific reasoning. This is done only based on based on my own preference. Okay, there's no other reason for reducing it from 300 to 250. I just feel a bit safer if I give 250. That's it. You are allowed to use such hunches when you do design. Okay. You can also just say 300 center is also fine. I have done a very perfect design. I know that nothing is wrong. So if you are very confident, go ahead with 300. If you are a bit wavering, you can be a bit safe and give us smaller spacing as well. Okay. So once again, these ties have to be given, and these are not spiral ties. So therefore, you have to make sure that all the bars are hooked together. Okay, so this is hooked. Similarly, inner bars have to be hooked together. Okay. So once again, these are okay. So this is the end of this particular problem. Somebody is not muted.
આખો દિન ગયા ને 10 મિનિટ ચાલે પાછું આપણે
Okay, so this is this way. The same problem I could have done with an arrangement like this. Table 44. I could also gone with an arrangement like this. Okay, so I hope you're able to see this picture. I could have arranged bars on all four faces as well. That is also an option. So if you had done that, you would be using this table instead of the previous table 32, previous chart. You'll be using this chart instead, and accordingly these values will change, and you'll be calculating a different reinforcement. Okay, so the choice is yours. You can use either this arrangement or what we did now in the problem. But among the two, what do you think is a better arrangement? Arranging equally on four sides, or arranging on the side with only two sides of reinforcement? Which is better, do you think?
Two sides, sir.
Why? So the final reinforcement which you calculate, the area of steel, will be more or less the same. Okay, more or less it will be the same. So on what basis do you say 2 is better? It's okay, tell you had some reasoning to say 2. So what is that reasoning? It's okay, I just want to know what logic you used. Tell me. Why did you say 2? Just why are you afraid to tell the reason? Tell me why did you say 2? Bas, the person who answered. Why did you say 2, Bas? Okay, where have you gone? You answered, you said 2, then I asked you a follow-up question, you are not answering. Are you still there or gone somewhere?
Well,
Okay.
there is less reinforcement in centers.
Less reinforcement in the, I mean, along the
More
depth.
space.
Okay, that's fine, but why do you say that is preferred? Okay, what I'll say is no, it's if you have see, if you have moment, if you have pure axial compression, giving it on 4 sides is best option. If you have moment along one direction, then it is better to give your reinforcement. You know, for example, here if my moment is since my moment is this way, okay, so I want to give sufficient reinforcement along this depth. Okay, so you're allowed to do that. It in many cases doesn't make much of a difference, but in many times what happens is in actual building column, you will not have pure uniaxiality. You will have many times moment along this direction as well. Okay, even if you call it as a uniaxial bending problem, there may be some moments which you do not calculate, which are caused because of construction clearances, tolerances, some eccentricity. So these kind of reasons, some minor moments may occur on the other direction. Some moments may occur, etc. So in many cases, also from the point of view of symmetry, it's sometimes a good idea to give uniformly on all the 4 sides. But if you decide that it's going to be a waste of money doing that, then you're allowed to just keep it along for 2 sides alone. Okay, it's just a balance between symmetry and economy. Okay, either of that can be used as long as you know that you are giving 4 sides or 2 sides reinforcement for a specific reason. Okay, as long as you know why you're giving it, you can give any of it. Okay, but anyway, so assuming that you decide to give it like this, you have specific tables which cater to 4 sides of reinforcement also. Okay, so this is one thing that you should know. The second thing that we'll see is we'll see a problem on biaxial bending, which is a little bit of an extension of this. Okay. Okay, so if the similar details will be given given to you for these problems also, you'll have an ultimate load to be designed for. Let me assume that it is about 2000 kilonewtons. Let me say mu x. Okay, one of the moments is let's say 100 kilonewton meter, and the other direction moment is about let me make it smaller, maybe about 50. Okay, so these are my moments and axial load. Okay, now once again I have axial load, I have one moment, I have another moment. So if I want to draw a rectangle, how do I draw this rectangle? Which way do I orient it? Which way do I orient?
Is higher, that direction we have to give more depth.
The direction of which MUX or MUY? So which should I take as x-axis? Which should I take as, I draw it like this. Which direction should I take as x-axis? Horizontal or vertical? Which axis is x-axis for me according to this?
Horizontal.
Horizontal. So this direction I will have to choose my x and y axis. Okay. By the way, one step I didn't tell you when doing the previous problem is even these charts also, they are for these charts are also for short columns and low eccentricity. So you remember those checks which you did, that L by D less than 12 and L by 500 plus D by 30, some number you'll get, and compare with 20 mm. That number should be lesser than 0.05 times the that dimension. So those checks have to be done before you actually start using these tables also. I didn't mention that. I forgot to mention it. I'm mentioning it now. Okay. So don't forget that these charts are all applicable for short columns of low eccentricity. Okay. So that should not be forgotten when talking about all this. So for this problem again, I'll probably use the same dimensions. Okay. I'll take 300 by 600 again. Okay, and also I will take, this time I'll increase the grades. Okay, I'll make it maybe M30 and maybe 500 because I have more load and more moments. So this is the grades I'm choosing. So this procedure has a little bit of extra steps. If you have biaxial bending, a little bit of extra steps are there. So I'll go to a biaxial bending chart first. By the way, uniaxial bending, you also have charts for circular sections, circular columns also. Same, so it's only differences. You'll have P by FCK capital D square and mu by FCK D cube. Okay, the axis only change, but the other things are same if you have a circular column. Okay, uniaxial bending. So anyway, let's keep going down for biaxial bending. What is this? Bending only. Okay. Where is that form? Oh, it will come before itself. Okay. Come and start. Reflection tables. Compression members. So let's have a look at the conditions for biaxial bending. Compression members subject to biaxial bending. So basically we're going to use the same charts and we are going to find the capacities of the moments and see that they satisfy this condition. Okay, so there are a few steps to be done before we use the chart. Okay. So first thing that we do is here we have a lot of assumptions to make. Okay. Previously we had assumed only the size and we didn't bother much about the reinforcement. We found the reinforcement in fact from the charts. Here we have a little bit of extra things to do. First thing that we need to find is we need to first find what the capacity of the given column is, and in this, to use this expression P U Z is equal to 0.45 FCKAC plus 0.75 FIAS. This to use this we actually need the area of steel. Okay, we need the area of steel to actually do this. So initially itself we will have to assume some steel has to be assumed at the beginning itself. Okay. So one particular easy way to do it is, I know AC. Okay, I can set a very high value of PUZ. Okay, and then find out some value for AS. So that is one option. Or for the given PU which I have, the 2000 kilonewtons which is given in the question. For that PU, I can find out how much steel I require and increase it by a certain amount, maybe to 1.5 times or 2 times, and then proceed with that reinforcement to find out these values. Okay, so I'll use this method and I'll proceed with it. Okay, so first thing I want to find is PUZ. So PUZ given over here is, it's easy to remember the formula. So there you had 0.4 FCK AC plus 0.67 FIAS. Here it becomes 0.45 and 0.75. Okay, the constants are not different because one of the because you have two directions bending, it's a bit relaxed from the previous formula. 0.45 FCK. AC is nothing but gross area minus area of steel plus 0.75 F by ASC. Okay, so among this I know everything. I have 2000 into 10 power 3. This is 30. This is 300 by 600. This is 500. Okay, find out what you get for ASC. Just see what you get for AC. How much do you get area of steel? It's PU, in fact, not PUZ.
Sir, 1189.48.
1190 maybe then. Okay. Okay, so he has got 1190. Now if it is 1190, one of the options that I can give, if I have, it's actually pretty low value for giving. So I have another thing that I should consider is the reinforcements. So obviously there will be 4 on the corners. So previously for uniaxial bending we gave 2 here. Okay, but here I have moment along 2 directions. So it's better for me to actually give it to be distributed this way. Okay, it's better to make it this way rather than giving it 300 by 600. It's not uniform. Okay, so only when I give it like this, I'll have more or less the same spacing between the bars. So it's better for me to give it this way because I have more moments, one more moment along the y direction also. So therefore I need to give the reinforcement, better to give the reinforcement on the 4 sides because of this reason. Okay, so total I have about 10 bars because of this. So 10 bars if I want to fit for 1190 mm square, then I would have about maybe 12 mm bars, 12 mm bars will be used. Okay, so but anyway, this 1190 which I have found is only counting for this PU. This has not been found by considering MUX or MUY. Okay, so as a preliminary reading, I can use this 1190 as a base. Okay, and probably make this much more. Okay, I got 1190. Maybe I want to give it about twice of this, maybe 2500 mm. Okay, so I'll probably say, let me give 10 numbers of 10 bars. So 10 numbers, if I say 20 mm, okay, this gives me about 3140 mm square. Okay, this is vastly different as compared to this. Okay, and you may be, when you compare this is really large as compared to what I got. And you may be wondering, should I actually take this much larger reinforcement as compared to what I got? Okay, unfortunately, it is always better to try a very high value of reinforcement compared to what you need for the axial load, because you are at this stage you are not sure how much reinforcement you will require to take care of this MUX and MUY. You are not sure at this particular point of time. Okay, or if you want to If you want to make it a bit more conservative, probably you can say 16 is 16 or 201. Okay, let's see. Okay, 2010 mm square. Let us see if this works. Okay, I think once if you do it only, you will understand what the problem is. Now, PUZ is nothing but the actual capacity with the reinforcement that you decide to provide. It's basically the same formula. Use the same formula. Instead, this time you substitute this value as 2010, the one which you decide to provide, and find out how much PU you require. Okay, find out how much this comes. Okay. Actually, in many cases, you can avoid this step, directly assume the reinforcement and try this. But if I didn't want to directly tell you that. Sir, good afternoon. Sir. அதான் அது பார்த்தேன் அந்த நீங்கள் அது வேற ஃபார்மேட் இருந்துச்சு. ஸோ நீங்கள் அமிச்சிங்களா அந்த ஒரு மினிட்ஸில் வந்து இந்த நியூ எலக்டிவ்ஸ் நியூ ஹானர்ஸ்லாம் போட்டிருந்தீங்க இல்லையா? ஸோ அதை மட்டும் அப்படியே காப்பி அதை மட்டும் நெக்ஸ்ட் காப்பி பண்ணி அந்த ஃபார்மேட்டில் போட்டு சாருக்கு அமிச்சிட்டேன். இந்த ப்ராப்ளம் இல்லை. ஆமாம் சார், நீங்கள் இந்த பிஓஎஸ் அந்த ஸ்லைடு வரும்போது நீங்கள் தான் சார் சொல்லணும் அந்த மாதிரி வந்து இந்த சேஞ்சஸ் பண்ணுறோங்கிற மாதிரி. அதான் சார், அவ்வளோ 2 minutes 3 minutes தான் சார், வேறு எதுவும் ரொம்பலாம் கிடையாது. 2-3 minutes ஃபஸ்ட்டு ஜஸ்ட்டு இது மாதிரி இது சேஞ்ச் பண்ணிருக்கோம் சொல்லிட்டா போகிறோம்னு நினைக்கிறேன். இல்லை சார், அவங்களே பண்ணிடுவாங்கன்னு நினைக்கிறேன். நான் சிவசங்கர் சார்ட்ட வேணா கேட்டு வேணா உங்கள்கிட்ட சொல்கிறேன். இந்த மாதிரி வந்து அவர் பண்ணி வச்சுட்டாருன்னா வேணா அந்த ஸ்லைட் அவங்கள்ட்ட காமிக்க முடியுமான்னு வேணா கேட்குறேன் ஜஸ்ட்டு முன்னாடி ஒரு வாட்டி. சரி சார், அவர்கிட்ட கேட்குறேன் சார் நான். ஓகே சார், தேங்க்யூ சார். How much do you get PUZ?
3156.6 kilonewton.
3157 kilonewton. Okay, fine. Super. Now you got PU by PUZ. The next thing that you need when you look at this, when you look at that, going too fast. Okay. You need this value PU by PUZ. Okay. Initially, you would need this value. So PU by PUZ. Based on that, you will be calculating a certain coefficient. So this can be calculated at this stage, or it can be calculated later. But anyway, it can be calculated at this stage. PU by PUZ is PU is the actual load which is coming, and PUZ is the capacity of the column for pure axial compression for the given reinforcement and size. So how much is this ratio?
0.633.
0.63. Okay. So this is the ratio. This is the interpolation value. 0.2, it's less than 0.2, it's 1. If it's greater than 0.8, it's 2. So it's going to be somewhere in between. So probably you can, so less than 0.2 is less than is 1, and greater than 0.8 is 2. Okay, so you can interpolate it. So basically I'll be getting 0.43 by 1 into the point, this is by interpolate பண்ணுவாங்க. y2 minus y1 இது வந்து 0.63. Okay, 0.43 about 1.8 you will get, I guess. Just check. Get alpha to be close to 1.8. So those who are faster than me, if you have found out what the coefficient is, you can tell me. If you get close to 1.8. Okay, let me keep it as that and keep proceeding. Somebody can tell me later if it's close to that. And then the next things that we need is we need MUX1 and MUY1. Okay, we need two values. Okay. So to find out MUX and MUY1, you will use the same charts. So if you just read this, you will know what they mean. So MUX, MUY are the moments which are actually given due to x and y, about the x and y axis. MUX1 and MUY1 are the uniaxial moment capacities when an axial load PU is acting about the x and y axis. Okay, so in fact you're doing a bit of reverse as compared to what you did for the uniaxial bending problem. So I'll have to now use the table for four sides reinforcement, and I have to go to FE 500 and I'll use this table. D dash by D in for us is 0.83 or something, so I'll use D dash by D is 0.1. FI 500. Okay. Now among this I can find out PU by FCK BD. Okay. So PU by FCK BD. And I think the previous problem itself we had found. So this is 2000 into 10 power 3 divided by FCK. I think it's 30 M30 concrete M30 into 300 into 60. 600, sorry. How much is this? And find this, and then also find PT, which is equal to 2010 by 300 into 600 into 100. Okay, PT by FCK rather. So into 30. So find out these two things and tell me. These are two numbers that you will need for calculating MUX and MUY1.
0.7 and 0.037.
0.7 and 0.037.
0.37, 0.037.
0.7 and 0.037.
0.37, sir.
0.37, okay. And this is 0.037.
Yes, sir.
Okay.
Alpha n is 1.7, not 1.8.
1.7, okay. Okay. So now we have a value of PU by FCK BD and PT by FCK. Okay. Now I come back to this chart. I do the reverse. I actually pick a value of PT by FCK. So my PT by FCK is 0.037, which is somewhere close to 0.04. Okay, so somewhere below that I'll probably take about this point. And PU by FCK BD is also 0.37, meaning that it's somewhere probably this point. Okay, and this point, if I just go down, I see that my 0.037 is probably here, and 0.37 is also probably this. So from that, from the PT by FCK value of 0.037 and PU by FCK BD value of 0.37, I convert probably somewhere over here. It's coming about MU by FCK BD square equals 0.07. Okay, it's coming something close to 0.07. So I get the current from chart number of the chart is 48. Okay. on chart 48, I get mu by FCKBD square equals 0.07. Okay, so from this I can find out what you should remember is we have found out this mu by FCKBD square value for a provided amount of steel, an actually provided amount of steel, and the actually applied axial load. So what I find out from this mu is basically how much moment along this x direction will this column take if there was only axial load and only this moment alone. Okay, so this is basically equal to my mu xu1 equals 0.07 times 30 times 300 is once. Now you come to biaxial bending, so you should be careful what you use for B and what you use for D. Okay, since this is mu x1, I will be using this as B and this as D. When you do mu y1, this will become D and this will become B. Okay, so that difference you should remember. Okay, so find out how much is mu x1.
$226.8 kilonewton meter.
226.8. Okay, we may be a bit tight. So similarly, we can do mu by FCK. So basically it's the same chart which I'm going to use. Okay, it's the same chart because everything else is same, except that now because I'm looking at mu y, my B becomes D and D becomes B. Okay, so I'll say B square D equals 0.07, giving me mu y1 equals 0.07 times 30 times 300 square times 600. So how much kilonewton meter? So mostly after
113.4.
how much?
113.4.
So mostly when we finish this problem, when we do this next step, you will understand that why we need to take a much higher quantity of steel than what we require initially itself. So the next step is what we have to do is we have to actually use the interaction equation. So what is an interaction equation? This is an interaction equation. Okay, so this is known as your interaction equation. Okay, so you can either use this equation or you also have the option of using chart 64. Okay, so both are given to you. Okay, do you remember seeing these pictures when I was covering the theory for columns? What is this diagram called? You remember what this diagram is called? Okay, let's come back to this. So I'm going to now check my interaction equation. So my mu is 100 kilonewton meter and 50 kilonewton meter. Okay, so mu x is 100 kilonewton meter, mu x1 is 226. My alpha in value is 1.7. My mu y is is 50 kilonewton meter. Mu y1 is 113.4. This power 1.7. How much is the result of this?
0.497.
அவ்வளோதான் வருதா? அப்படியா? ஓ, only 0.497. ஓகே. 113.4. Oh, okay. So 0. Yeah, get about 4.497. Okay, actually fine. Actually, what we given is quite decent enough. So basically speaking, yeah, I'll come back to that, no problem. This, if you look at this equation, we have to satisfy that this summation should be lesser than 1. If it's greater than 1, then something has to be increased. Either you increase the reinforcement or you increase the size of the column. Okay, something has to be done in case this had actually come less than 1. Okay, so this is less than 1. So therefore, dimensions and reinforcement are sufficient. Okay, so this is it's sufficient as long as you have this thing with you. Okay, so yeah, so this is how you actually design a biaxial bending problem, where a lot of it depends on the initial assumptions that you make, the initial dimensioning that you make. And so as I told you, if you can initially just find out what reinforcement you require only for the axial load and increase it by a certain factor. Or if you are if you're experienced enough and if you are able to make good guesses, you can avoid the step itself. Okay, and you can directly just assume some reinforcement and check with it. Okay, so this it's basically more than saying design. It is more like you yourself at the start itself say that okay, you're going to try it out with certain dimensions and certain reinforcement, and based on that trying out which you have done, you just use the CEPC16 to check whether whatever you have tried is okay or not. Okay, this is not like for beams where you exactly find out, calculate certain values, and then based on those calculations you are doing the design. This is a little bit reverse of that. You initially itself you decide the dimensions and check whether they are okay. Okay, it's like an anti-design. Okay, and so you can do that, or you can use 64 chart also, where things are a bit slightly easier. So these charts have MUY by MUY1 and MUX by MUX1. Okay, so basically MUX by MUX1 is about 100 by 226.4 to 6.8. Okay, 0.44. And this also actually MUY by MUY1 also comes in this case the same value. So this is 0.44. My PT by FCK is 0.037. Okay, my PT by FCK is 0.037. And okay, not PT by FCK, PU by BZ. PU by BZ is 0.37. So I just have to look at that and see whether I fall within the range. So PU by PZ 0.37 is this curve. Okay, you can take the 0.4 curve. This is the curve that your point should fall inside. Okay, so this curve is here. My MU by MUY1 0.44 is somewhere over here, somewhere along this line. And my MUX by MUY1 is also along this line. Okay, so it falls within the curve. So basically, basically what you're doing is you're choosing that curve. So based on the PU by PZ value, you choose a certain interaction curve. Okay, and then here is MUX by MUX1. MUy by MUy1. And then you know these values, you just plot that. You plot that point and see whether it is falling inside the curve. If it falls somewhere outside, then you are unsafe. Okay, which corresponds to a case where this would have exceeded 1.0 if it falls outside the curve. Okay, so this is the process of designing a column for biaxial bending. Okay, so I'll give you some things to read. Okay, so you will also have some better familiarity in solving these problems. I'll stop with this for today's class.